Have you ever considered how electrical engineers unravel the mysteries of invisible magnetic fields, especially around current-carrying wires? It often feels like a daunting task, full of complex equations. But there is a remarkably elegant shortcut. Amperian loop symmetry is incredibly important because it allows us to drastically simplify the calculation of magnetic fields. It transforms what would be a challenging integral calculus problem into a straightforward algebraic one, making solutions much more accessible. At the heart of this simplification lies Ampere's law, one of Maxwell's fundamental equations. In its general form, it states that the line integral of the magnetic field B around a closed loop is directly proportional to the total current enclosed by that loop. Now, performing a line integral, especially when the magnetic field varies in both magnitude and direction along the path, can be quite complex. This is where symmetry becomes our powerful ally. When a current distribution possesses a high degree of symmetry, such as a long straight wire, a tightly wound solenoid, or a toroidal coil, we can intelligently choose an Amperian loop that mirrors this symmetry. For example, around a long straight wire, the magnetic field lines from concentric circles. If we choose a circular Amperian loop coincident with one of these field lines, two crucial things happen. First, the magnetic field strength, B, is constant everywhere along our chosen loop. Second, the magnetic field vector, B, is always perfectly parallel to the small displacement vector, dl, of our loop. This means their dot product, B dot dl, simplifies to just B times dl suddenly. The complex integral of B dot dl around the entire loop becomes just B multiplied by the total length of the loop, which is its circumference. This simplified expression then directly equals mu0 times the enclosed current. This remarkable transformation from a difficult integral to a simple algebraic equation is why symmetry is not just helpful, but absolutely essential for many practical calculations in electromagnetism. So, for you, recognizing these symmetric configurations is key. When you encounter situations like a very long solenoid or an infinite current sheet, immediately look for the corresponding symmetric Amperian loop. Select a loop where the magnetic field is either constant and parallel to the loop or perpendicular to parts of the loop, making the dot product zero. By carefully choosing this path, you can bypass pages of complex vector calculus and arrive at an accurate magnetic field strength with surprising ease. This elegant approach isn't just a mathematical trick. It forms the bedrock for understanding many fundamental electromagnetic devices. Before the advent of powerful computational tools for numerical methods, exploiting Amperian symmetry was often the only practical way for engineers to design and analyze components like transformers and inductors. While today's tools, such as finite element analysis, handle truly arbitrary geometries, the insights gained from these symmetric solutions remain invaluable. They provide quick estimations and build your intuitive understanding of how magnetic fields behave, a skill for beyond simply plugging numbers into software. It's truly an insider detail for anyone deeply studying electromagnetism. Ultimately, understanding Amperian loop symmetry allows us to conquer seemingly intractable problems by finding the hidden order within the chaos of magnetic fields. It empowers us to simplify, calculate, and ultimately design with confidence, making the abstract principles of electromagnetism tangible and practically applicable in the world around us.